In a previous video, we discussed about quorum, we learned about quorum and how it can help consistency in a distributed system. Now let's talk about an interesting scenario when quorum gets sloppy, and we will specifically talk about sloppy quorum and hinted handoff. So let's get into it. Let's try to understand what is the problem with strict quorum. And let's first again draw the diagram which we drew first for the strict quorum scenario. So let's say there are 5 servers. Out of them, 3 can accept a particular write. In the last video, we saw that W plus R greater than N, and in this case, N equal to 3. That means that all of the write requests has to be acknowledged by W number of replicas. All the read requests have to be accepted by R number of replicas, and the sum of W plus R has to be greater than N, which is 3 in this case, in order to make sure at least one of the reads has the latest data. Now let's imagine that out of the 3 of them, one of the servers goes down. Actually, let's say 2 of the servers go down. In that case, what will happen? As per the strict quorum rule, the system cannot proceed because the write request won't be accepted. The read request also can't be accepted. Let's say we chose W equal to 2 and R equal to 2. So both the read and write requests will fail because we have only one required server that is up, the other 2 are down. Please note that these 2 servers are up, but these 2 servers do not accept a particular write. Let's say I am trying to update a balance of account A, and as per the database partitioning, account A data only is replicated across these 3 servers, and these 2 servers do not accept the write. So if the required servers, the number of required server, it goes down, then we can't read or write based on the configuration. So this is a problem, especially for highly available scenario. If we need to accept a lot of writes, we can't block the writes indefinitely and wait for the servers to come up. And this is a very common scenario because in distributed systems there are a lot of replicas, and each of the replicas, they can communicate among each other in different patterns, and network outage can always occur, and this scenario is very common. What is the solution? The solution is sloppy quorum. So in the previous example, even though these 2 servers are down, what we can do is we can configure the system to continue accept writes, and these 2 servers, which are originally not meant to accept write for a particular account, they will rise to the occasion and start accepting the writes. So instead of writing to W required replicas, the system writes to first W healthy nodes it can find. And then this includes a substitute node like server D that is not a part of the original replica set. So as you can see, these 2 servers are not part of the original replica set, but they rise to the occasion. And what is the most important result? The write succeeds and the application remains available to the user. Now, of course, this is not the ideal scenario. When these 3 servers, 2 of them went down and the other 2 servers, they accepted the writes. Now when these 2 servers come back up again, there has to be a mechanism where the temporary servers that accepted the writes, it will transfer those writes to the original replica, and that's what happens in hinted handoff. In this case, the substitute server that stores the data along with a hint that it actually belongs to the original servers, and when the original server recovers, the substitute node just hands off the data it was holding, and this is a background process that heals the system and moves it back towards consistency. So what's the trade-off? Of course, this is a deliberate trade-off. The sloppy quorum is a deliberate trade-off, and we are prioritizing availability. As you can imagine, because we could not proceed further with the write request, we opted for this sloppy quorum strategy, so that if any other server can accept the write, we allow that to happen and unblock the write request. And then during a failure, the read request must hit the original replicas and miss the new data stored on the substitute node. And this is a form of eventual consistency where the system becomes fully consistent only after the handoff is complete. As you can imagine, after the original servers have recovered, they might not have immediately handled or gotten back all the data using the hinted handoff. And in those scenarios, the read request might fail Or even in the previous example, the read request can go to these some other servers and which might not have all the original data, and that might be inconsistent. When do we use it? There are some real world examples. For example, if there is an e-commerce shopping cart, it's better to save the item to the cart and sync later than to fail the add to cart action, because if a customer is trying to buy something and then they can't add something to the cart successfully, there are very high chances they will not go ahead with the purchase. So it is better to save the item to the cart and sync later. Similarly, social media likes or comments where consistency is not very important, we can capture the user's interaction immediately as the priority. And then in the session data, we can ensure that user session is saved is essential for application usability. So a quick recap. What is a sloppy quorum? What is the advantage of it? It keeps write operations available during server failures by using substitute nodes. And hinted handoff is a background repair process that moves data to its correct home once the failed server recovers. And the result is a highly available self-healing system that favors eventual consistency. Even though the consistency is not strict immediately, we trust the system will be eventually consistent. So this is a quick video that focused on the sloppy quorum and hinted handoff. Hopefully you liked the video and the content has been useful to you. Please like the video and share the video among yourselves, and also subscribe to my channel. See you in the next one. Thank you.